Hi guys, welcome back to Biology Videos at TDA. We're going to do resting potential and action potentials in this video, which is 13.4 from the Caboodle textbook. Some jokes here, I'll let you get them later on. There's two kind of main sections we're going to look at, and our objectives by the end of the lesson is to understand both resting potential and action potentials. And you should be able to go through the steps off by heart and then kind of be able to apply it to an exam question. So we're going to start off with resting potential. You need to kind of see them at the moment as two separate things, and then you kind of see how they interact later on. So, resting potentials. So for our electrical impulses to go down our neurons, we need to have some kind of mechanism for it. And this is an example of the cell membrane of an axon in a neuron. And we need to be able to pass that signal down, and the way that we do that is through a wave of excitation, and we'll come to that shortly. But what we have to do is you have to set up this wave. So if you want something to move in the form of a wave, you need to have the energy set up in some way. And this is how we do it. So when we're not conducting our impulses, we prepare our ions around the cell membrane of our axons to be able to diffuse through. And in the basics of it, the way it works is sodium and potassium move in and out. And when they move in and out, that changes how electronegative the inside of the axon is. Now, at rest, normally, a number you do need to know is minus 70 millivolts, so a thousandth of a volt, 70 of those. And that is around, and it can range almost up to about 90 millivolts, minus 90 millivolts, down to minus 40, depending on the cell. But the number that we use is minus 70 millivolts. And we do this by something called a sodium-potassium pump. I'm going to show you more. And by doing that, we create this thing called an electrochemical gradient. Now this is, see it as a force, and I'll go into more detail. It's like a push between lots of sodiums, or lots of the same chemical being positive on one side, and that kind of pushes down to the other side, and that creates a force, and we'll come to that a little bit more. So how do we do it? I found this is the best image I could find regarding from my textbooks regarding kind of keeping everything in place. So I'll try and go through it. So this is an axon. This is the cell membrane, the phospholipid bilayer, is exactly how you've learned it so far. It's just cut off the screen here, but this is the extracellular fluid in blue. So this is outside the cell, and then this is the cell cytosol, so inside. Now, just to notice a few things, on the inside we've got some negative proteins, so we refer to those as anions. And one of the kind of key ways that this works is these anions can't move out. We remember large proteins generally can't get in and out of cells. So these anions that are negative, which helps keep the inside of the cell negative because we want to maintain minus 70, they stay in. The things that do move are sodium and potassium. And we've also got, this image is quite good for showing chloride ions. So we have lots of sodium and chloride ions, which are in abundance, lots and lots of these in the intracellular fluid, which is, as you know, it is salt. So we have lots and lots of this, and when it's in solution, they then become ions and they can move. So we also have these channels. Now these channels they can open and close, and they can allow sodium to rush in and potassium to rush out, and that's how an action potential is going to occur. Now, their leakage, now what that means is they can leak through. They're not being pumped, they're going to passively diffuse through. Okay? Now, this image is trying to represent that. There are more sodium leakage channels than there are potassium leakage channels, which means you're going to have more potassium leaking out than you're going to have sodium leaking in. We've also got something here called a sodium-potassium ATPase pump. And the reason why it's called that is it requires ATP, and we're going to be moving 3 sodium out and 2 potassiums in. So, how does the process work? So we want minus 70 in the middle, and the way that we achieve that, and this goes on all the time, is sodium-potassium ATPase pumps are requiring energy to actively transport 3 sodium out for 2 potassiums in. Now they're both +1 charge. So this means then, as this is working, and this is working at all times, it's always going, that means then we're pumping 3 out compared to 2 that we're pumping in. So I'll try and show that. This is another image that I kind of made. So whilst this is going on, now I know it's not showing on this image, you're moving 1, 2, 3 out, whereas you're only moving 1, 2 in. And if you repeat that and repeat that, you end up with lots of sodium on the outside, lots of potassium on the inside. Now that means for every 3 compared to 2, if I go back to this image, that means then you're going to have a difference of +1 outside per pump, which means you're going to end up with a slightly negative centre, which is what we want. So this is how we achieve that. Also, okay, the sodiums that leak in, because there are more the potassiums that come in, because there's more potassium channels that leak out, that means we've got this electrochemical gradient where these potassium ions, imagine that they repel each other and they then also leak out. So you can see these kind of pyramids here that are leaking back out. So not only are we pumping out lots of plus, you've also got some of these other pluses, because they repel each other, they also go out. That makes the centre even, the cytosol even more negative, and then you've also got these anions, these proteins in there already. So this is how we achieve the resting potential. So the thing to kind of write down if you're making notes on this is the 3 ways we achieve it is, first of all, we have an unequal distribution of ions from the extracellular fluid to the cytosol. So point number 1, 3 potassiums go out 3 sodiums go out. Again, just correct and follow if I've said it wrong. 3 sodiums go out, whereas 2 potassiums go in. 3 sodiums out, 2 in. And that's the first way that we achieve it. The second way is that these anions can't leave the cell, so they keep the cell cytosol negative. And then finally, you've got this leakage of the sodium. You've got more leakage of the potassium compared to the sodium coming in. So you've got more, and it isn't directly a 2 to 1. Don't learn that number. You need to learn this 3 to 2, but you don't need to learn this number. What you do need to know is that there's more potassium leaking out than there are sodium leaking in. So they're the 3 ways, and this is how we get the cell axon ready to do an action potential. So if you want to learn this now, a good thing to do is pause the video and go and kind of make points on this. If you go to the Caboodle textbook, it's kind of documented here as well, and there's a little image as well that says that. Okay, right, so let's move on to an action potential. Okay, so let's have a look at the action potentials now then. So we've got to the point where we know that the resting potential has been established. We've got more sodium on the outside than we have potassium on the inside, and we have more potassium on the inside than we do on the outside. So we've got it set up. Okay, so we've seen before, we've got this 3 to 2 sodium, potassium, ATPase. I thought I'd just show you this animation as well to kind of give you another version of looking at it. So you can see energy is required, active transport, 3 out for every 2 in, and we've also got the extra leakage. And there's a figure here, you don't need to learn it, but you can see there's a lot more permeability to potassium than there are to sodium. So potassium moves out of its gradient back out again. Okay, so let's have a look at the actual nerve impulse itself then. So we've achieved our resting potential, we've got negative on the inside and positive on the outside, and the way that we work this out is we can use a microelectrode. So when we're talking about potential difference, so millivolts, we're looking at the difference in the electrical charge outside compared to inside, and we can do this with tiny little electrodes that can detect it. So action potential, we've got our uneven distribution. So what's going to happen? So the first step, for whatever the stimulus is to cause this to happen, we don't really need to know now. But the first step that's going to happen is sodium voltage gated sodium channels are going to open, and that's going to cause an influx, or a rush of sodium ions into the cell. So that's the first thing that's going to happen. So the sodium channels are going to open. Now we call this stage depolarization. Because we're currently polarized, we're currently slightly negative, and we're going to then stop depolarizing. Now for most neurons, that will be around minus 55 millivolts. That's the threshold. And that's the idea of the all or nothing. We'll come to that again later. Is that unless we reach minus 55, these gates won't open because they're voltage gated. They need to hit a certain voltage for them to open. So when they hit minus 55 millivolts, they're going to open. And all the sodium is then going to rush in. So we're going to depolarize, and this is then going to cause a change that's going to go from minus 70 roughly. It hits the gated channel at minus 55, and then it's going to then go to positive, plus 35 millivolts. Okay. Now when this happens, this kind of causes a wave. So as the voltage gated channels here start to open, and then they're going to start to cause the sodium to rush in, that's going to then cause the next one to open, and the next one, and then the next one, and the next one, and then this continuous changing of the potential difference across the cell membrane is going to then cause the next set of gated channels, voltage gated channels, to then open. Okay, and it's really very quick, as you can see, 0.5 milliseconds. So, first step was depolarization, sodium moved in. Now we're going to open up the potassium channels, so they're also voltage gated potassium channels. They're going to then open, and then the potassium is now going to rush out of the axon. So we have depolarized, now we are repolarizing. So we were polarized before in the resting state, and then we depolarized, so that means all the sodium rushed in, and now we are repolarizing, so all the potassium is rushing out. And this causes the net movement of ions again to be moved. So we're going to then change it, rather than being negative on the outside, we're now going to be positive. Okay? Now, when this occurs, these potassium channels, it's described as sort of stay open too long. These potassium channels stay open for too long, which means it goes above the minus 55 millivolts. Sorry, the minus 70 millivolts, which is resting potential. So that's then going to go up to somewhere around 90 millivolts. Again, you don't need to know that number, but you need to be aware that the next stage is hyperpolarization. So you've got depolarization, repolarization, and then hyperpolarization. So we can summarize this now with a nice little image here. So we've got at rest, okay, we've got our resting potential achieved, we described it earlier. We're now starting an action potential, so a nerve impulse. So the first thing that's going to happen from minus 70 millivolts, a stimulus, whatever that might be, causes the sodium channels to open, and then we've got these depolarization. Then we're going to then get to a point where our voltage gated potassium channels are going to open. So we've got our sodium is going to rush in. Now that's going to stop, and the potassium is going to rush out in the depolarization. This now is going to happen up to back to 70, and then it will go just beyond that. And that's going to then stay open for too long. Potassium channels stay open too long, so then that's going to cause hyperpolarization. And that's the end of the action potential. And then at this point we have something called the refractory period. And what that means is, at this point here, before we get back to rest again, we can't do another nerve impulse. Okay? Now if you have a really strong stimulus, getting close to the 6 here, you can have another one. Okay? But there's a little area called the absolute refractory period, which means no matter how big the next stimulus is for the next action potential, you won't have another impulse. So we have some terms here, let's kind of define them. We've got our threshold value, which is minus 55 millivolts. So this has to be reached for our action potential to occur. And we refer to this as the all or nothing principle. Without a big enough stimulus, it might go from minus 70 to minus 60 to minus sort of 58. But if we don't reach that threshold point, all the sodium channels aren't going to open. We call that the all or nothing principle. Okay, And again, the usefulness of that is it stops neurons firing from very small stimulus. Kind of what I was talking about last lesson, where if something very, very light lands on your skin, it will be detected, but it won't cause an impulse because there's not a big of a stimulus. Now, once that's passed, we've got this refractory period. So this refractory period is a delay before you can do the next impulse. Okay? It also ensures, another kind of key point, is that we have unidirectional impulses. It means that neurons always go one way, okay, and they always go down one direction. And then you have it's not mentioned here, but you have the absolute refractory period, which means that even if a strong stimulus comes on, you still can't. So there always has to be a little gap in time. Now, the speed of these impulses can be affected by a couple of things. We looked at saltatory conduction previously, so that's myelination of the neuron. And this jump, again, I apologise for the language here. You can write jump in the exam, but it'll be ignored. What you need to say is myelination causes a local current, which increases the rate of transmission. And there's a couple of other things that also increase it. So the axon diameter. So the larger the axon diameter, the faster the rate of conduction. And then finally, temperature for basics of ions moving faster. Okay, so there's quite a lot to learn in this, so I'm going to do some quick questions, and I'm going to put a couple of exam questions in, and then I'm going to give you a task to do, rather than lots of exam questions. So, I'll go at these questions, pause the video, and write them down. And the next set, again, pause the video. Okay, the answers, again, I'll just let you pause the video, so you can mark your answers. I've got a couple of exam questions, but they're relatively short ones, so you can have a go at this. Now, be really careful, think about repolarization, which section was repolarization, and then you can think about the channels. Okay, so that was A, so we've got the repolarization, so that's when we've gone sort of up the graph, and then we're going back down again. So the sodium channels are closed, and the potassium channels are open. Okay, and then the membrane potential is quite confusing because you've got to think about it's going more negative, so it's actually decreasing. This is quite a good question, so take some time to have a think about this one and have a go. So, when are the voltage-gated sodium ion channels open? So, from both B and C. When is repolarization? So, that's from D to E. And this is quite a good question. Sodium ions are actively pumped out of the neuron, so that is the maintaining the resting potential. So, you should have written all the letters down: A, B, C, D, E, F, G, or you can write. Final question, I quite like this one, have a read through and have a go. So some kind of explanation, so why do we not generate when we have clothes on? We kind of forget that we've got clothes or glasses or our watch on all the time. And the idea is the sodium channels are being stimulated, so they're always open, so we're not actually getting back to this resting potential, so we can never produce the next action potential. So you stop detecting it. So the idea is the ions are in the wrong place. The reason we need to re-establish this resting potential is because we've just moved all the sodium in, all the potassium out, and we know that's not where we like it with the resting potential. We like to pump the sodium out and the potassium in. Okay, some short questions. So what I suggest you do now is bullet point how we achieve a resting potential and bullet point the process of an action potential. Maybe draw the graph and bullet point the different sections. That's quite a good task. There's lots of YouTube videos, loads and loads and loads on action potentials. If you haven't got it, understood it from the way I've explained it, here's one example. But if you simply type in achieving rest potential A-level biology or action potential A-level biology, you'll find loads. Thank you very much. If you could upload your upload your pictures to the work that you've done to share my homework. Thank you.